In this last video, I want to go through a few confusing issues that comes up with these topics. And again, just differentiating or distinguishing between mass, gravity, and weight is confusing. And we're using these very specific definitions in physics class that might be different than your everyday definition. For instance, the first big confusing thing is that kilograms are units of mass, pounds are units of force. Now within physics class, where we use SI units, the units of force we would normally use are newtons. However, in the English system, when you're measuring in, feet and whatnot, you use pounds. So the point is that if you're an American and you are standing on an American scale, you are measuring pounds. It's actually wrong to call that mass. That literally is a measurement of force. So calling that, oh, I have measured my weight, that's actually accurate. On the other hand, if you're a European or someone from Africa or Asia who uses a kilogram scale, in that case, then you aren't actually measuring your weight when you stand on it. So notice that some scales might actually tell you both pounds and kilograms at the same time. Those don't even measure the same thing. So this is another way to think through the fact that your bathroom scale is kind of lying to you, in that kilograms are units of mass. And so if you're standing on the scale and it's telling you kilograms, it has already divided out gravity for you. It's made an assumption about what's happening with the forces. An American scale in pounds is actually lying to you a little bit less. So be careful about that. That can just be confusing in terms of newtons. The unit for mass in the English system is slugs or something. I don't know. I don't know. I only use SI units for this reason. Okay. The other thing which I have clarified but is important enough that I want to come back to it again is that on Earth, gravitational force depends on mass, while gravitational acceleration is constant. And again, in the gravity section, I actually went through that in detail, so if you skip that and this is surprising to you, you might want to go back and watch that. And this again matters because if you just say gravity, and you say, well, gravity is constant, well, did you mean force or acceleration? So we're now at the point in the class where it's really important to clarify when you're talking about gravity, are you talking about gravitational force? Or are you talking about gravitational acceleration? Since those are two different things, one depends on mass and one is constant. Okay, next, and this is something the book brings up that I didn't go into detail in or mention at all until now. There's actually a correction to G when you calculate it from the Earth mass and radius. So earlier I talked about how you can go from universal gravitation to Earth gravitation by plugging in a bunch of constants. You get a number that is ever so slightly, less than 1%, different than what you would calculate this way. And the book says that it's about the rotation of Earth, and that's fine. It isn't important. That's not something that we're going to bring up for a little bit, and so I don't want you to get overwhelmed by it. So G is still going to be 9.8 meters per second squared. You don't have to worry about whatever corrections you need to make to it. This is the value to use, so please don't get overwhelmed by that. If you think it's cool, that's awesome. It is really cool, but it's something that we'll talk a little more about later in this class, and then you'll study in much greater detail if you continue on to higher level physics. Okay. Next, again, I clarified what weight was because we're meaning it in this very specific way of what the scale measures. And so I'm using Knight's definition. In many other books, this gets called apparent weight. So if you've studied physics before, you've probably encountered this idea of scales measuring different values in elevators, but possibly in that case it got referred to as apparent weight. So here we're just calling that weight, but other places it gets called apparent weight. So be careful if you're using outside resources, other textbook, Google, other videos from outside my class or from Knight, because there will be a terminology difference here, very likely. Lastly, again, this is something the book goes into, and I'm only bringing up here in an attempt to clarify. Weightlessness doesn't actually mean there's no gravity. People think it does, and on Wikipedia you'll see references to that, but that's not true. What's happening is that the person is inside a container and both are in free fall. So we could think about this as an elevator, or typically you think about this as astronauts in the space station. They're not necessarily so far away from the Earth that there's no gravity whatsoever. That's not the case. It just happens that they are both falling together, and so you don't feel any push against a surface. So this is a situation where it's a little hard to think through, so I try not to bring it up. I'm not going to give you problems where we really think about weightlessness, but the main thing is to not think that, astronauts up in the space station have no gravity acting on them whatsoever. That's not true. So weightlessness happens when two things are in free fall. That could even happen in an elevator, but that would be really bad if you were in an elevator experiencing weightlessness. So to summarize, by giving you brief summaries of each of the definitions, mass is a fixed property of the object. If I have a block of 1 kilogram, that does not matter whether I am on Earth or on Mars, it is always 1 kilogram. Gravitational force is calculated from mass of the object times little g, where on Earth that is our 9.8 meters per second squared. And on other planets, it will have different values. Finally, weight is a measurement. In this class, we are using it to not mean either of these two things, but something different, and typically this is going to be given by a spring compression or the stretch of the spring, and it's going to depend on acceleration, which is why this is fundamentally different than the first two. It's true that you can use gravitational force to infer mass, and frequently weight tells you about gravitational force, but weight and gravitational force are only related when you have an object that is not accelerating.